this one before you turned it in. Yeah? Do this.
Are we gonna have time to
Yes, but I want to talk about the reactions with you. Because we get out at 8:45. It's 8:20, so we got time. That's yours, under your cabinet, yeah. Alright, so I'm going to conclude the reactions, and then I'll let you guys finish the analysis before you turn it in. But the reactions themselves, it's important for us to kind of talk about what actually reacted, talk about why it occurred, and then finalize reactions together. So in terms of doing that, you guys have your reactions listed out. You should identify the 4 types of reactions. I'm going to ask for different lab groups to help me out, okay? So, Robbie, y'all's lab group, tell me what happened in that first one. Actually, I'm going to just write on the smart board over here.
First one.
The first, part A.
Okay. The type of reaction was synthesis.
Okay, so why are you saying synthesis?
Because
Okay, so before I move to there, the only reactant was magnesium, right? It can't really decompose because it doesn't have a partner to break off from, right? So it's not going to be decomposition, because most of us are like, oh, it required energy or heat. It's decomposition. Or it caught on fire. It's combustion. Was combustion an option? No. So that's forcing your brain to go to synthesis. And so the other thought was like, what the heck is it combining with? Well, there's this great atmosphere around us, right? And so Robbie was like, oh, what is the gas that could be the one it was reacting with? And why'd you say oxygen?
because it was like gas around.
Okay, there's a lot of nitrogen around us too. There's some carbon dioxide, but we've never really combined a metal with carbon dioxide, but we have combined a metal with oxygen. Okay, so then you put O2. That's the biggest part. I got to pass back your all's problem set 11s. That is the biggest part you guys messed up on. Was, do you know that it's diatomic? Do you know your 7 diatomics? Yes, and if you know your 7 diatomics, if it's written all alone by its lonesome self, it has to have a 2. That's the biggest part we messed up on. So, and then I'm gonna let you guys figure out that product is. Okay, the number 2 Chem's group. That was Robbie's group. Never mind. Kyle's group.
We decided that it was a replacement.
Okay. And what was the what were the reactants?
Copper sulfate.
Copper what? Copper.
Oh, copper 2 sulfate.
Copper 2 sulfate. Okay. Copper 2 sulfate. And that reacted with?
Sodium carbonate.
That's copper 2 sulfate.
Not that. Iron.
Iron. Okay, that's why it's a single replacement reaction. So in this case, who was the active element? Iron was the active element. It did a single replacement. You saw that beautiful color of copper come out of the solution at the bottom. It was that kind of orangey brownish color. And this was what I was concluding with one group, actually a number of groups. This is copper 2. Copper 2 is blue. And that's the observation you made before the reaction. So you're writing your observations and everything down, right? You had all your observations, colors, and gases and everything made. So copper 2 is blue, and that was the solution. That was the color of this solution. Well, afterwards, you had this kind of like green, brown-ish colored solution. It was no longer blue, because all that stuff that made it blue was what? The copper 2 in the solution. But now that copper 2 is not in solution. Where's it at? It's at the bottom. Copper will be that solid that precipitated out. And then you have this leftover stuff. And I will tell you the most common charge of iron, if it's forming an ionic compound, the most common charge of iron is iron 3. So use that to form your final product as you do your single replacement. Iron will form a 3. All right, Miles, what was the next reaction? Miles group. So it was double replacement. And what were your 2 reactants?
BaCl2.
Barium chloride, BaCl2 plus. Beautiful. Sodium bicarbonate or sodium carbonate. And it does a double replacement. And what did you guys observe?
Highly liquid as well.
You saw what?
That's highly liquid, and then the product was sodium chloride and
Barium what?
carbonate.
Carbonate. And what's that formula?
BaCl2.
Beautiful, because the barium has a 2, carbonate has a 2, crisscross down, 2 goes to 1, 1. And actually, it's probably was hard to see if you didn't let it settle, Who let it settle? You can see that difference. Did you see that white powder on the bottom? It's hard to see because it suspended itself pretty at first a lot, but it did. That was what was precipitating. I did take the solubility rules off your desk. Sorry, but that is carbonate is the one that is precipitating there, and you would balance that for your observations. And then lastly, Jacob's group. Last thing.
Decomposition.
It was really by default, right? We only had one option left. But what was the reactant?
NaHCO3.
All right, there's that bicarbonate. Remember, the bi in the front means that it has an H plus in the front, so carbonate has an H in the front. So that's bicarbonate. And then what were some observations you guys made? Audrey, what was an observation you made with that one? Would you just give me any observation you saw with that decomposition? What happened to your stick? Fire kept going out, and you guys wanted it to catch on fire, but it just wouldn't. So what gas could be being made that would cause a fire to be extinguished? Rishi. Carbon dioxide, right? And that is what's in my lovely fire extinguisher over there, right? It's compressed carbon dioxide, and I blow it on the fire. Carbon dioxide is heavier than air, and so it smothers the fire, puts the fire out. So we know that was the gas. What else did you guys see forming on the test tube, on the glass itself? Some people saw a yellowish thing. That's because it was burning, but that's okay. What else? What vapor? CO2, you can't see that vapor. It was water vapor. Okay, so water, H2O, CO2. I know right now you're like, oh, that's combustion. No, okay, there's something else that's being made. So kind of let's fill in the blanks here. What else could be made? And I'll tell you, FYI, elemental sodium, just straight up Na, is really, really flammable and reactive. Like it would catch on fire in air. So it's not just elemental sodium, it's something else. Maybe a metal oxide. Let's see if that even balances. If we make, what would the metal oxide's formula be? Na what? Na2O, because sodium has a 1 charge, oxygen has a 2 charge, crisscross is a 2 and a 1. Let's see if this balances, and then that will allow us to see if that's truly the product. So I have 1 sodium, 2 sodium, so what would I need to do? Put a 2 here, and then that 2 distributes everywhere, right? Okay, so there's 2 sodiums, 2 hydrogens, 2 carbons, and 6 oxygens. Do I have 2 hydrogens? Yes. Do I have 2 carbons? No, so what do? 2 in front of the carbon dioxide? Okay. How many oxygens do I have on this side? 2 times 3, right? That's 6. That's heated, okay. And then how many total over here do I have? 6. 2 times 2 is 4, plus 1 is 6. So is that the right formula? Probably. All right. It could also have made sodium carbonate. Actually, sodium bicarbonate breaks down into either sodium oxide or sodium carbonate, actually at different temperatures. So really hot temperatures make something different than really kind of medium to hot temperatures. So we're going to go with this for now because it actually worked out. All right. So I'm going to let you guys kind of conclude on that last little bit. Maybe for about 5 or 6 minutes to work on the conclusion questions. And if you guys need to go with your groups, do that. I have one more thing for us to talk about today, and that's about it. So once you're done, you can put your labs in the box. If you are done, then I'll give you the next part. Let me grab this for you. You don't need to do the intermediate. This is from 2 days ago, from today and today. Yeah, you can do that. I'm going to put the solubility rules like right here in front of Ayana if you need to borrow them for one of those questions.
I was still talking about the list.
What the flaming says to indicate, I give you this, I give you this explain all three flames plus what gases are they detecting or observations for the flame to occur. So the flames are going to indicate gases that are present. And those are the three gases that you need to know what happens when those. Guys, on number 4, if you are confused still, number 4, I'm asking you about the flame test, right? But I'm already actually in that parentheses telling you it's indicating for gases. Flaming smoke test indicates for gases. But there are 3 different gases that they can detect. And during those 3 gases detecting, certain things happen with the flaming splint. Those are the 3 gases, H2O2 and CO2. When the flaming splint comes into contact with those 3 gases, different things occur, and that's what you're describing for me. 2 of which we saw today, 1 of which we saw in the NIE lab that Nick and Robbie showed us with the zinc, mossy zinc, and the HCl reaction. When you guys are done, you will see I put a worksheet. I want you guys to do the first little bit of worksheet on the desk that's around you someplace. Do not write on my worksheet. Do some things you can.
It makes it hard to get
Alright guys, at this last 10 minutes of class, listen for me. You have a basic stoichiometry model worksheet near you. You are not writing on this, you're going to write on your own paper. If you don't have one near you, please ask for me for one. But right now, you're starting this. You're at least going to get 1 through 5 done. 1 through 5. You have 10 minutes. And we will finish this on Monday, but I want you to get a start. One through five. Talk in your groups about it as well.
So it's a 1-to-2 ratio. So 1 to 12. Yeah.
Oh, you got it. Maddie, focus, honey. I've heard this conversation for the last 5 minutes.
Because it has a 2 or 1 to 2.
All right, I think your conversations are actually working really well. I want to hear a little bit more about your saying though, because I heard some good things. What did you guys say for what do the coefficients of a balanced chemical equation represent? How many moles it takes to combine them, right? You could say number of molecules, or you could say number of atoms, or you could say number of formula units, but you're narrowing down to like a specific particle. When A, I don't know, A could be a atom, a formula unit, or a molecule. So to represent the natural equivalency to that using Avogadro's number, you could just say number of moles. So it is the number of moles it takes to combine to make this recipe work, make this reaction work. All right, and I hear some good things with number 2. Who has a good thought process in number 2 so far? Jillian.
Well, you can use the model to create the
Okay, so she's saying this model here These, they just make conversion factors by using what? The coefficients to compare different things. And is there a relationship up here that pulls together A and D?
For every 2 moles of A, products for moles.
Okay, so for every 2 moles of A, it produces 4 moles of D. Where are you getting this from? Okay.
And then you 2 on the bottom since you're trying to cancel out moles of A.
Okay, hold on. Pause on that moment for that for just 1 second. Does everybody see where we got this? So there are 2 moles of A according to the recipe, and that forms 4 moles of D according to the products of the recipe. So we can actually, we have the power, we have the knowledge to make our own conversion factors, which is great because we don't got time to write all these out all the time, right? We can just pull the coefficients and call them a combination or a ratio. So then tell me how you're starting this conversion. What are you starting with on number 2?
So first you start with the given.
You're given, which is
You
what?
have 6 moles.
6 moles of A.
You're using that conversion factor you created.
Okay, how am I writing it?
So you have to write 4 moles of D on top.
Okay.
2 moles.
And so this is an equivalency that we created because it makes sense according to the recipe. And we want to get 2 moles of D, so we put moles of D on top. We want to get out of the unit of A. And so what we have been doing in the past is not really always identifying the identity of what we're talking about. So we have like a unit, but we didn't say what it was referring to. But now we have to write down what it's referring to. Because moles to moles, you're like, what am I talking about? I'm going to say moles of A to moles of D. It's very, very specific. Do you see the significance of that? So moles of A cancel with moles of A. And so how many moles of D could be created here? What's 6 times 4 divided by 2? 12. 12 moles of D. And that makes sense because of the ratio that we established. And if you recognize it just by logic, for every 2 moles of A, I make 4 moles of D. Well, I'm just basically making double D, right? Making double of D. So if I had 6 of A, it makes sense I make 12 of D. Give me a thumbs up if those ratios right now makes sense-ish. Okay, so that's basically what the rest of this worksheet is, but I'm not going to have you do the rest of this right now. You guys have this that we're going to kind of finish up on Monday, but this is what we're jumping into with all 4 feet on Monday. We're taking reactions. I gave you a fake reaction up here. We're going to take real reactions and work through some stoichiometry. So before I finish this, write this on your paper. Tell me the 3 mole relationships one more time. 1 mole can be converted to what, and what? Formula units, atoms, or say again? Molecules, and those are all called what? Those are all, what's the big umbrella term? Those are all particles, okay? So particles are converted from mole, sorry, what's the relationship between these? Avogadro's number, 61022 times 10 to the 23rd. And then what's the next conversion? Mass, and how do you get to mass? Molar mass, and how do you get molar mass? Well, periodic table, which is, yes, moles per gram, or grams per mole. Okay, and the last one? Liters, and how do you get to liters? 22.4. Okay, and that's at SCP. So, go ahead, and the paper that I passed out to you last, that is yours. You guys have a 20-minute video that you are watching, and on the video I have exactly the notes in the upper right-hand corner. Do you see the notes in the upper right-hand corner that say the driving forces lecture notes? Do you see that? Driving forces lecture notes. This is your copy to take home. The worksheet you were just working on, please don't take. That's my class set. There should be enough of these at your middle table, the middle of your table. Because you guys need 1 more for free. Okay, this is yours to take. Does everybody have one of these? Say yes or no. Yes. So you can make a note that you are going to take notes from this little section right here. Go ahead and pack up one. Good. So video on driving forces of action, what that is, and keep looking at the ice brainstorm. Yes, sorry. Last thing I'll say, it's not on Monday by any means. We're not going to be ready probably till Wednesday for this. Wednesday or even Thursday. We are going to do a stoichiometry lab. Bring stuff for s'mores. I'll keep reminding you every day. more geometry. You see how that works? Boom, as much as we can. EJ, are you good here?
I'm good.
Thanks, man.